Speaker is Regilene Oliveira from ICMC-USP. She will talk about PC and the problem for some polynomial differential systems.
Thank you, Ronaldo. I also would like to thank the organizers for this opportunity to speak here in this meeting in honor of Federico. And to start, I would like to say congratulations, as we say in Portuguese, Feliz Aniversario. So I speak about B-center problem for some polynomial differential systems. This is a joint work with Wilker Fernandes from Universidade de São João del Rei in Brazil and Valery Romanovsky from Maribor, Slovenia. This is the outline of my talk. I will start with an introduction, then I will tell a little bit about the approach that I use to study the center and the linearizability problem. And then I will explain how to use such approach to study the simultaneous existence of two centers in a planar polynomial differential systems. And to finish, I will present some references. Okay, the main goal of my talk is to discuss a method to investigate the existence of two centers, or in fact two simultaneous centers, and two simultaneous isochronous centers for some families of planar differential systems. Let me explain a little bit the idea and why I intend to study them. A polynomial differential system, in general, I could write as x dot equal to p, I dot equal to q, where p and q are real polynomials in the variables x and y, and we say that n is the degree of such systems if n is the maximum between the degree of p and q. So to each vector, I would say it's better to say in this way, ordinary differential equation is associate a vector field that I denote by x, given by p xy ddx plus q xy ddy. So this means that each solution of these systems, that is a curve, gamma 1, gamma 2, is the same that the integral curves of this vector field. In the same way, we could associate to this vector field, and also for the system, one differential form in the plane that is, in the sense that Professor Ionescu told us, a form given by, let me say, p dy minus q dx. So here, if you consider the set omega equal to 0, we have leaves. Each leaves is the same that the integral curves and the solutions. This is why we are in the plane, okay? This is not true in other spaces. Okay, so my idea is to discuss a method to decide when such systems could have two simultaneous centers and two isochronous centers. The main idea is the following. I'd like to investigate what kind of properties the parameters of these systems must to have for this happens. And in fact, I'm interested in the geometry, in some properties that I could investigate in more general way. I hope to become this clear till the end of my talk. Okay, so let's consider a planar polynomial differential system, x dot equal to u, y dot equal to v, and suppose that the origin is a singular point, a singularity, for which the eigenvalues of the linear part are purely imaginary. So this means that the origin is not a hyperbolic point, so I cannot use the Hartmann-Grobman theorem. So the behavior nearby of this point can be or a center or a focus. And to decide if it's a center or focus is what we call the center problem or the center focus problem. Okay, from now on, I will use this fact that after a change of coordinates, each system in this way could be written as this form. Maybe it's better here. X dot equal to minus y plus, let me put here, what means PQ of x, y, where q is going from 2 to n, where n is the degree of the system, and y dot equals to x plus q from 2 to n, where PQ and QQ are homogeneous polynomials of degree k. Okay, so the center problem is a problem that was investigated by many authors. Here I'm giving you some examples. So, for example, Dulac have studied the quadratic systems in 1908, Malkin the homogeneous cubic systems in 1964, Chavarriga and Ginet the homogeneous quartic and quintic systems, and more recently Faircheck and et al. Homogeneous quintic complex systems. Let me say now what means isochronicity. So if all periodic solutions in a neighborhood of a center possess the same period, I will say that the center is isochronous. Probably, I don't know, I try to discover something about this, but the first mathematician that has studied the isochronicity was Huygens, that was a mathematician in the 17th century. And the problem to decide when a center is isochronous or not is what I usually say this isochronicity problem. Okay, so again, some examples of authors who consider this problem. Huygens, studying the pendulum clock. Laud, the quadratic systems in 1964. Pelskan, Chavarriga, Romanovsky, Ginet, et al. It's important to mention that in the same case of the center problem, these authors have considered the center problem and the isochronicity problems, but they use completely different methods, okay, different approaches. So this means that you could investigate for many different ways. Okay, so what is the approach that I would like to present to you here? The approach for the center problem is the following. The key result is what we call the Poincaré-Lyapunov theorem that says the following. System one for me is this system. So system one has a center at the origin if and only if admits a first integral of this form. So I will denote by phi. Another way to say that is that phi satisfies this condition where this x is exactly the vector field that I put here, okay? So it's important to mention that a first integral for system 1 is a function that is not constant, but that is constant on the trajectories of the system. Okay, so now sometimes I don't know what to say with so many things. And okay, so let's consider phi as in the previous form, okay? And work with system 1 in a recursive process. So we could write x phi in this way. I choose a specific form to write the expansion. So each one of these v's are polynomials on the coefficients of the systems. So this means that they depend only of PQ and the parameters of PQ and QQ. And I will call them the focus quantities, okay? So it's important to mention that the vanishing of all focus quantities is the necessary sufficient condition for phi to be the first integral. So we call the Baltin ideal to the ideal generated by the focus quantities, and the variety generated by this ideal is what we call the center variety. Okay, so as I told before, the vanishing of all focus quantities provide us the necessary sufficient conditions for the existence of a first integral for the system. So our main objective here is to find an irreducible decomposition of such variety, what looks like a little difficult because we have infinite numbers of focus quantities, but this is not true because of the Hilbert basis theorem that guarantees that just a finite number is enough. Okay, so in practice what we do is the following. We compute the first any focus quantities, then we find the irreducible decomposition of the variety VBN, that is the finite ideal, okay? For this we could use the routine means GTZ of singular. Then, in this way, you could obtain the necessary conditions for the existence of a first integral. To prove the sufficiency, we show that each component of the reducible decomposition corresponds to a system that possesses a first integral in the form that we want. Okay, this looks like beautiful, but what happens when we are doing the computations? Usually we cannot complete the computations for any example. So sometimes we need to use what we call the modular arithmetic decompositions, because in this case we could work in a field of a finite, in ZP in fact, okay? So here the idea is to choose a P, a very big prime P, then compute the reducible decomposition of such variety over ZP using the same routine. Then apply what is known as the rational reconstruction algorithm to obtain what could be the equivalent conditions, but to be sure that they are okay, we test if the obtained decomposition belongs to the center variety. If yes, okay, we could follow. If not, we must choose a new prime, probably a big prime, to start again. Okay, suppose that we check and we got the good conditions, so we could check if the center variety belongs to the irreducible decomposition. I will show you in details when I will apply these techniques for an example. But I will return a little bit. So this is the methods to obtain the necessary conditions. But what to do to prove the sufficiency? Then we could use two different methods. We could use what I called the Darboux integrability theory, that consists in to find enough number of invariant algebraic lines. So phi I equal to 0 is called invariant algebraic line if satisfies x phi I equal to chi I phi I, where this is also a polynomial but could be complex in the variables chi I. This is called the cofactor of phi I. So I'm using I because here I need a finite number of invariant algebraic lines. So suppose that I could find such a number, a finite number of algebraic invariant lines, such that this condition happens. So the Darboux integrability guarantees the existence of first integral of this form. Another possibility is to find an integrating factor that consists in to find enough number of invariant curves such that this happens. Another method is the time reversibility that consists in to verify if there exists a line, here I'm denoted by L, such that the phase portrait of the system is reflected by L with the sense of all orbits being reversed. Okay, so this is the approach to study the center problem. Now I will show you that you could use a similar approach to study the isochronicity. In fact, the isochronicity is equivalent to the linearizability problem. This is came from this result that says the following. The origin of system 1 is an isochronous center if and only if there exists a change of coordinates, look here, is very specific way, such that the system 1 is linearizable. So here again, I work in the same way. Suppose that there exists such change of coordinates. Let's derivate both sides and use some equalities, and then we could find in a recursive process some polynomials on the conditions of the coefficients of PQ and QQ, such that the change of coordinates exists. So again, we have some polynomials that I would denote them by IQ and JQ, and I would say that such polynomials are the linearizability quantities. Okay, so now I could repeat. Let's take the ideal generated by them, the variety generated by this ideal, and the vanishing of all linearizability quantities is the necessary condition, is sufficient conditions for the existence of the change of coordinates. So again, we could apply the irreducible decomposition, and from the Hilbert basis we know that it's necessary only compute a finite number of such polynomials. In practice, we could repeat the same steps, okay? The difference here is that to compute to prove the sufficiency, we use another methods that is called the Darboux linearization methods. That is, again, we use the cofactors and the first and the invariant algebraic lines. This is the main result. So system 1 is linearizable or Darboux linearizable if and only if there exists enough number of algebraic curves such that the following properties happens. So look that here is not any algebraic lines. We must have specific forms satisfying a specific property, but this result give us exactly the change of coordinates, okay? Okay, so this is the approach. Now, how to apply this approach to study the problem that I'm interested in, that is the simultaneous existence of centers. To start, I would like to mention some authors who consider this problem. Sibirsky have studied the quadratic systems in 1978. Conti have studied the family of cubic systems in 1988. Sheng, Lu, Wang, Liu, and Li, and Du also have studied such problems, but again, the approaches are completely different. But I would like to emphasize that in this paper, they have considered the Z2 equivalent cubic systems. In fact, I will study the Z2 equivalent quintic system. So this paper was the motivation for our work, okay? But they used a different approach than the one that I will present for you here. So let me say what means a bicenter, okay? So a differential system is called the Z2 equivalent with respect to the point P if its Friese portrait is unchanged after a rotation of angle pi around P. And suppose that system 4, I will denote here, system 4 is Z2 equivalent and has two singular points that here I denoted by A and B, that I know that they are centers. I will say that A and B are B-centers if system 4 is Z2 equivalent with respect to the middle point of the line segment AB. So it's like a mirror, okay? It's just a symmetry that will reverse the sense of the orbits. Okay, so my objective here is to study this system. Let me show you the conditions over it. So x1 and x5 are homogeneous polynomials of degree 1 and 5. P and Q are symmetric points with respect to the line x equal to 0, so this is my line, and they have purely imaginary eigenvalues in its linear parts, what means that they could be center or focus, and the system 5 is Z2 equivalent with respect to the origin. So the question is, what are the conditions over the coefficients of this system such that this system has a bicenter? Okay. Okay, before to go, it's good to say that this system has 16 parameters, okay? So what is too much? So the first step is how to decrease the number of the parameters, because with 16 parameters I cannot apply my approach. So this proposition that gives us a canonical form and says the following: System 5 is the system that I gave you before, has two, suppose that system 5 has two singular points with purely imaginary eigenvalues on its linear parts that could be arranged in the points -1 and -1, 0 and 1, 0. Then there is a change of coordinates such that the system could be written in this way, where I have only 10, I have only 10 parameters, okay? Okay, it's better than 16. So the idea now is to find conditions on the parameters, on the 10 parameters, for the existence of a bicenter and isochronous bicenters at these two symmetric points. Okay, but the problem is that 10 is too much yet. So I cannot study such family in just one way. So the approach was the following. The idea is to study some subfamilies in order to get the information about whole family as soon as possible. No? But okay, let's say that the computations done here were performed in a machine with these characteristics. So maybe if you have a better machine, you could have better results, okay? Okay, let's start. Let's show you some results that we could get with the approach that I have described before. Okay, suppose that system 6 is the normal form that was in the previous proposition, okay? With A1 equal to -1 and A5 equal to 0 has system 6 with these two conditions has a bicenter at the points -1, 0 and 1, 0 if one of the following conditions hold. So let me explain a little bit how we get this result and why only if and not if and only if. So the idea, the proof is the following. First, we compute the first 9 focus quantities. Here I'm showing you only the first 2 because the third one takes more than 1 page. But it's good to see that they depend only of the parameters of the system. And then we compute the reducible decomposition of the variety VB9 using the routine of singular. But here we must use the modular arithmetics. We provide these conditions using this big prime. And after the computations we get for ideals. Okay, after rational reconstruction, we get the conditions that is in the previous result, and then we try to check if these conditions are the right ones, but we cannot be sure. So we check if it's possible to have the same conditions using different primes. So we apply, for example, for this prime that is bigger than the first one, you get the same results. Okay, so we conclude that these are the unique conditions with a high probability. Okay, we cannot say that they are in fact because we cannot get the last step of the modular arithmetic algorithm. Okay, so this is why if, okay? The if that you have in the statement of the main result comes from this fact. Okay, now we must to show that the sufficient is of the obtained conditions hold. So we could check that for the first, third, and fourth case we have an integrating factor, and that in the second case the system is time reversible. So in fact we could say that we have bicenter under that conditions. Okay, so now the idea is to try more subfamilies, but due to the complexity of the ideal B9, we are not able to perform the computations using our computational facilities. So let's see what happens with the isochronous centers. So now the result is the following. For the same system, with the same conditions, we don't have isochronous bicenters. This happens following similar ideas. We computed the 9 pairs of linearizability quantities. We computed the reducible decomposition. Then we put here the ideal V9 and the condition that we get in the previous result. Okay, this is the first condition, theorem one. Sorry, and then the conclusions that this is equal to 1. So we don't have isochronous bicenter here, and also in the other cases. Okay, we have 4 cases, and in any one we could find conditions to the existence of isochronous bicenters. Okay, so let's check what happens. If the conditions in the state 1 are necessary and sufficient for the existence of a bicenter for system 6 with these 2 conditions, when A1 is equal to -1 and A5 is equal to 0, then such system cannot have a bicenter. And this sounds a little strange, because in the case of Liu and Li, where they have studied the cubic systems, they have centers that are isochronous centers. So let me show you. So here, this is the picture, okay? So these are 2 examples of isochronous bicenters where Liu and Li got in their papers, okay? It's interesting because they are, we don't have just a bicenter, but we have 3 centers, okay? And in fact, we could prove that they are isochronous. So we have not 2 centers, we have 3 centers, and all 3 are isochronous. So the question is, could this happen in the case of degree 5? What could be the conditions on the coefficients such that this happens? So we try to look for other cases. So here I put exactly what I have discussed now. So the idea is to try to fix different parameters. So let's start with some possibilities, okay? Instead of to fix 2 parameters, let's try to fix only one. And this is a good result, because system 6 with A2 equal to 0 has an isochronous bicenter if these conditions hold. So, okay, we could get a condition to have an isochronous center. The way to prove is similar from the previous one, okay? But I would like to see that here A1 is always different of 0, and even the same for A7. A3 sometimes could be different of 0, sometimes could be 0, A5 could be 0 or non-zero. So a natural question is, could exist another condition different of A2 equal to 0 such that system 6 admits a bicenter, an isochronous bicenter? So we cannot apply our approach for these conditions, okay? We are not able to perform the computations. So we start to look for the space of parameters. And we check that if A1 equal to different of 0 and A7 different of 0, we are in the previous result. So if you would like to find a different conditions, then they must to be in the complementary. So this means that we must to fix A1 equal to 0 or A7 equal to 0. As we are not able to compute the reducible, we cannot apply the approach with only one parameter, we decide to fix two parameters. So we choose 15 conditions, okay? We get 15 conditions where at least one of them is A1 equal to 0 or A7 equal to 0. And the result is the following. System 6 satisfying one of the conditions from 1 to 15 has non-isochronous B-center at the points -1, 0 and 1, 0. So it's natural to conjecture that if A1 equal to 0 or A7 equal to 0, system 6 does not have anisochronous centers in such points. Of course, that I cannot state that this is true because I studied the case where at least 1 is 0, but sorry, I cannot study the case where just 1 is 0, but if 1 is 0 and one more parameters, okay? So this is just a conjecture. And if this conjecture is true, then we could say that system 6 has an isochronous B-center only if we have the conditions in the theorem 3. Okay, but why I have done such a study? The idea is to find the geometric aspects that could be interesting to study in order to get general results, not just for degree 5 or degree 3, but in more general cases. And the one thing that we could get from the study of the cubic case and quintic cases is the following. Under each one of the conditions from 1 to 5 in this theorem, system 6 is reversible. This also happens in the case of degree 3, okay? So it's natural to ask if the existence of isochronous B-centers at such points for this system implies in the reversibility of such systems. I don't know to answer this question till now, but I hope to be able to apply another approach in order to study not just the quintic systems, but polynomial systems, maybe to conclude things about. Another possibility is to study the existence of isochronous B-centers, not in the case of Z2 symmetry. But because here the symmetry is with respect to a line. But I'd like to see what happens if instead of a line, I have a curve, a non-singular curve. What happens in this case? Could I find conditions to have B-centers and isochronous B-centers? So these are some open questions about this subject. And to finish this work, we decided to study a little bit of the global phase portrait. So here we could see the global phase portraits from the conditions, to the systems described in theorem 3. There we have 5 conditions, but in fact only 3 non-equivalent global phase portraits. Here they are in the Poincaré disk. And here also I have something interesting, because look that in this case, in fact these cases are the same that we could find in the paper of Liu and Li. They didn't work in this way, but we did. And they have exactly these 2 forms. And now we get one more. Here, we never have just a B-center. We have always 3 centers, 3 isochronous centers. And the maximum number of isochronous centers is 5. So my question is, if I decide to study the systems with degree 7, I will have one more phase portrait with 7 centers, isochronous centers. So my question is, if I would like to say the minimal and the maximum number of centers and isochronous centers that such systems could have, this is the minimum 3 and the maximum is the degree of the system. So these are some questions that came from these papers. In fact, what I discuss here are part of these 2 papers. And this is the book of Romanovsky and Schaefer, where you could find more details about the approach using computational algebra to study dynamical systems. Thank you for your attention.
Are there any questions, comments? No more.
Hungry?
Excuse me, there are examples in which there are exactly two centers?
In this case, in degree 5 and degree 3, in any case, we have 3 centers, and all of them are isochronous centers.
More comments? Okay, let's thank Regilene again.
Thank you.